Hello, everyone. My name's Louis, and I graduated in 2024 with an ATAR of 99.55. And for chemistry, I got 49 out of 50 in the EA, which was this paper right here. And I'll do a part of the paper, just a multiple choice paper one from last year. And then adding on to my internals, I got 99 out of 100. She left me with 99% for year 12 chemistry. And so I'm doing this video because I want to help you guys. This was actually recommended by several people on my Insta page to do a chemistry video tutorial to help out with past papers and how to tackle chemistry problems and how to get a score similar to how I did. So I'll be talking through my thought process throughout this video. And just let me know in the comments if you have any suggestions or any questions. I'm happy to help. And I'll usually respond as soon as possible. So question 1 to 2, it's like a combined scenario, and then we have both question 1 and 2 related to each other. So we have the hydrated copper sulfate and its decomposition when heated. So hydrated copper sulfate, which is basically just copper sulfate and water with a dot in between, decomposes to form copper sulfate and water when heated. Right? So essentially, what we're just doing is we're heating this hydrated copper sulfate and then we're combining them. Sorry, we're separating them um, into these two separate components. So the question asks in question 1, which of the following is exchanged with the surrounding environment when copper sulfate, H2O, so the hydrated copper sulfate, is heated in a closed system to establish dynamic equilibrium. Right. So the key word here is a closed system. Now, it involves you having to know that in closed systems, and this is one of your dot points as well, but you need to recognize that in a closed system, only energy, so just heat, is exchanged, not matter. So as you can see, H2O, a gas, is a matter. It's a gas, so a matter is in terms of like solid, liquid, gas. And so since H2O is matter, it's not included. So I'm sorry, I didn't meant to circle that, but it's so not supposed to be B. It's not C because we have matter again. We have a solid and a gas, and then we do have heat, but we also have this solid, so that's also not allowed. So the answer is A. Okay, so just make that very clear. The answer is A there. Question 2. Determine the oxidation number of sulfur in CuSO4H2O. Okay, so oxidation numbers are the numbers we put in the top right hand corner as like a it's like a power when we for the element. So we know a couple of key assumptions. So we know that O in this case, because it's on the right hand side, we usually have the this sort of uh, we would call this the reducing agent because it gets oxidized right here. And then in green, we have the oxidizing agent, which gets reduced. Okay. And just remember, how I like to remember it is that agent is like allowing the other one to be reduced, which means that we have to get oxidized. And this gets reduced. So essentially what it means is that we're going to have a positive oxidation number for the oxidized elements, and then we're going to have a reduction in, sorry, a negative oxidation number for reduction, because it's the opposite. So one of the key assumptions we know is that the oxidation number for oxygen is -2. And how do we know that if we want to double check? Well, if we go to page 5 with the atomic and ionic radii of selected elements, we also get given the charge of the ion. And usually the charge of the ion is typically what it will usually have as its oxidation number as well. So we know oxygen, the only number here is 2 minus, okay? So that's the charge. We use in charges, we put the number first and then the symbol. But for oxidation number, we put the sign first. Sorry, it's meant to say sign. And then the number. Okay, but they're essentially the same thing, you know, most of the time. But there are exceptions, such as in this question, which I'll show you. But however, we know that there are 4 oxygens, right? So what we need to do is that we need to do O4 oxidation number is -2 times 4, which is -8, right? Okay, and then from that, we got to determine the oxidation number of sulfur. Now, lucky for us, we have multiple choice options, so it can really just be process of elimination here, right? So we also need to think of copper, right? So what oxidation numbers can copper have? Well, it usually, unless it's specifically stated, it usually has, it's definitely a reducing agent, which means it is oxidized, and we can prove that here, where it says in the formula sheet that copper here in element 29 is either 1 plus or 2 plus in terms of charge, so therefore +1 or +2 for the oxidation number. So we can have +1 or +2. So we need to figure out, well, is it +1 or +2? Okay, more likely it's going to be +2. Okay, that's just its usual, it's more probable, but I know some of you can might be a bit confused or not really easily accept that you just have to know it's +2, because what if it was +1? But there's a way to cancel out that it can't be +1. It has to be +2. Okay, there's a way to do that, and it's through the multiple choice options. So let's just say that, yeah, it is +2, okay? So if copper here is +2 oxidation, and our O4 is -8, and the overall oxidation number. Now, to know the overall oxidation number, it will show you in the equation, okay? So if there's no overall oxidation number, which should be in the top right-hand corner, such as here, like X marks the spots, then we know that if there's nothing there, then we literally just assume that the oxidation number is 0, okay? It's like for H2O, for example, we just assume that if there's no oxidation number given, sorry, oxidation number, we have the sign first. If there's no oxidation number given, such as +1, if it's just empty like that, like this equation, we know that O is -2, and we know that H is +1. These are their oxidation numbers. So we have two H's, like H2 in H2O, then we just timesing that by 2, so we have a +2 oxidation number, and oxygen has the -2, and when we combine them, +2, you know, obviously 2 minus 2 is 0, okay? So that's why it fits with our equation here, okay? But we're essentially just trying to find the individual oxidation number of sulfur, okay? So that's what we're basically doing here. So is there a oxidation number specifically stated in this part for copper in the hydrated copper sulfate? No, it doesn't have anything, so we assume that the overall oxidation number is 0, okay? So basically, if we just wanted to um, rewrite this again, but with our oxidation numbers and a question mark for the sulfur, because that's what we're trying to find, then essentially it's just basic algebra, okay? 2 plus something um, plus minus 8 equals 0, all right? So obviously this plus minus would become a minus 8, so 2 plus something minus 8 equals 0. We have just doing 2 minus 8 is negative 6 plus something equals 0. And that something, if we just add 6 on both sides to get rid of this here, to leave the question mark on one side of the equation, we have 6. Okay? And that's obviously a positive 6 because there's no negatives in my answer. So the answer there is B. Okay? If I were to choose plus 1 as my copper oxidation number, so say you're just looking at the formula sheet and you don't know whether to use plus 2 or plus 1, if I used plus 1 here, and then I combine my plus 1, negative 8, I get negative 7. And to get 0 overall, I need to make this sulfur plus 7. However, that's none of our options here. We have plus 8, but it's not plus 7. So it's definitely, copper is definitely not going to be plus 1. Okay? And most of the time, it will always be plus 2, unless they'll give you something like copper I or something. Which this I is, and it's a Roman numeral, but it essentially just tells you the oxidation number of them, okay? But most of the time, especially for copper sulfate, copper is always 2 plus, okay? So I guess what can also help is being familiar with the past papers of QCAA. I'm sure there's many times they've used copper sulfate, and they've, given answers on what they expect you to know the charge of that you know, uh, compound. So I hope that helps for those two questions. And we'll move on to question 3. So identify which of the following is an essential component of an electrolytic cell. So voltmeter, no, not really, because it measures the potential, but is it really an essential component for an electrolytic cell? Not really. It's just a measuring tool. Okay. When it asks for an essential component, we need to ask ourselves what is needed to drive the reaction. Okay. Like what do we absolutely need to drive that reaction? All right. So in terms of electrolytic cells, we know that they need an external power source to drive non-spontaneous reactions. Okay, so the defining feature of an electrolytic cell is that it is a non-spontaneous reaction, which means that we can't just put two substances or elements in a cell and expect them to automatically react. We need something external, such as a power supply, which is our answer. And I'll get to explaining that, to essentially, it's the essential component of the electrolytic cell in order for the electrolytic cell to work in terms of what we want it to do, to like transfer parts of its compound and exchange that. Right? So you can also do process of elimination here and see that uh, for the salt bridge, that's only needed in voltaic cells. And the standard hydrogen electrode is used for standard potentials, but not in electrolytic cells. Okay, so it's really, I guess, obvious by this point that we need a power supply in order for this electrolytic cell to work. Everything else is not that essential or important compared to the power supply. Question 4. Identify which polymer contains a carbonyl, which is a C double bond to O group. So polyester, so the keyword being ester, is just a um, carbon that is attached to a double bond to oxygen and an R group, and that gets polymerized. So that's what this will look like here. Okay, and so that is our answer because it has esters always have that double bond there to the O from with the carbon. So this would be a carbon here in that skeleton structure. Ethene would just have a double bond, um, and same as propene. So there's no double bond to O, and then same with tetrafluoroethene. So that's just double bond with I believe it's just 4 carbons and something like that. Um, yeah, but either way, there is no oxygen in either of B, C, D, so we know it's just immediately A. Titration is a volumetric analysis method used to, and then we just have to find what the answer is. Question 5. So it's not necessarily to measure the pH of an analyte. Um, this we already sort of know the volume of a titrant, but C is the correct answer here because we are wanting to calculate the concentration of identified solution. So if you remember about graphs, maybe from your um, IA1 data test, we remember that our titration curve, so it'd be more something like that. We basically titrate to find the concentration. Okay, so using this formula and stuff, so we have this point, is the middle, and then we're just calculating, pH, concentration. So it's really just, I guess, one of your dot points you need to know is just the purpose of a titration. But yeah, that's really, I guess, the purpose of doing that, you know. Um, I guess another explanation for it is that A is in terms of measuring pH of an analyte. Well, you can actually just use a pH meter. It's not the main titration aim. Because you can see in the question, it's asking titration is a volumetric analysis method used to, and that used to is the purpose, which is the what is in question. Okay. Same with the determining the volume of the titrate. Okay, you measure the volume, not determine something. Preparing that it's actually a very separate process. before titration. Okay. You wouldn't say to someone that, or in your IA2 student experiment, um, titration is used to prepare a standard solution of known concentration and volume. That's not, it doesn't make sense in that form. No, it won't be D because it's something we do beforehand. You could mention that by preparing a standard solution of known concentration and volume, titration can occur. But this question 5 is asking, what is this volumetric analysis method used to do? Okay, it is to calculate concentration of an identified solution. Okay. Question 6. The equivalence point of an acid-base titration occurs when right? So at this equivalence point, for example, here, I'll just move this graph down. We know that the titrant completely neutralizes the analyte. Okay, so just think equivalence is like chemically equal. Okay, so basically what that means is that 50% of the analyte is acid, 50% analyte is basic or base, acidic. All right, so 50% acidic, 50% basic, and they are caused by the titrant that we are trying to use to neutralize the analyte. Okay, so neutralize means that we have equal proportions of acid and base. Okay, because neutralize, we know that neutral pH is just 7, which is between the 1 to 14 pH scale from really strong acid to strong base. All right. For the other options, if you want to cancel them out, pH equaling pKa, that's actually called the half equivalence point. All right. So you should just know that. And B is pH stops changing. Not necessarily because like you can see if this has pH on the y-axis, which it does, and then we have the volume titrated. We can see that at the equivalence point, that's where it's really rapid in terms of the pH changing. That's like the maximum rate of change there. So it's not B. And then C, the indicator changes color. That's really about the end point, not the equivalence point. Okay. Equivalence point is more of a chemically equal, um, like chemical value or like observation, scientific observation, rather than a visual, a bit subjective or like outward observation, if that makes sense. So when the indicator changes color, we recognize that as the end point. So that could be like, depending on what indicator we use, that could be here at this point or here, but we like to keep it near the equivalence point. So it's more effective in telling us a good concentration calculation that's more accurate. You know. And the question 7 is, which option is a principle of green chemistry? Um, well, the answer here really is just A, and the reason for that is green chemistry. If you just think of green as less waste, less energy, few steps, Okay, chemical derivatives is really about um, you know, like um, derivatives. They sort of like just create waste. So they're essentially byproducts of the chemical, original product. So if we are avoiding chemical derivatives, we're essentially, um, you know, waste. We're avoiding waste here, all right? And green chemistry actually aims to reduce those byproducts. Option B, where it says decrease energy efficiency, actually we want to be more efficient, so that's the opposite. Option C, prevent catalytic reactions. Actually, they're encouraged because that will make the uh, reaction faster and less requiring to produce more waste products and things. So again, efficiency and atom economy um, is should not be minimized. It should actually be maximized. So the option is not D. So it has to be A. Okay, atom economy is just basically saying, you know, um, I guess it's sort of like a percentage of like how much we are retaining from the reactants to products. Like how many atoms are we retaining and are not going to waste. So, if we have a really low atom economy, then that means we have a low, mm, I guess, it's low efficiency as well because we've lost a lot to um, from the reactants going to the products. We've lost a lot that isn't actually useful, like a byproduct or waste products that aren't useful for the actual um, reaction to create the products. But if we maximize atom economy to say more like 95%, then that's really good because that means 95% of the reactants actually went into the making the products, okay? As opposed to say 65% atom economy is going to the products. Okay, so that 35% is just wasted, like it's useless, basically, for this reaction. Okay, so question 8. Determine the IUPAC name of the organic compound shown as above. Right, so we know that there's 1, 2, 3, 4 carbons, so it's going to be butane, but that's all the options, so it doesn't really help us at all. But what matters is this um, key feature, this group here, where we have a C double bond to O and single bond to O. And then with that single bond of C to O, we have H thereafter. And so that shows it's going to be a carboxylic acid. Okay, because we have the COOH. All right. And so it's going to be definitely butanoic acid. All right. That was an easy one. So just recognize that if we have a COOH, we immediately think carboxylic acid. Okay, butanone is a ketone from the one. Butanol is an alcohol from the ol. And butanol is a aldehyde. So think aldehyde. So none of these are carboxylic acids. Okay, if we have an oic acid in the name, that means it's a carboxylic acid, such as propanoic acid, butanoic acid, pentanoic acid. Okay, oic acid is a carboxylic acid. Okay, Those imply each other. Question 9. Polytetrafluoroethene, PTFE, has a higher melting point than polypropane, PP, due to the... Right? And then we have to figure out what's the best answer here. So we'll just go from A to D. Option A says CF bonds being non-reactive. Well, not really, because bond reactivity doesn't really impact the melting point. All right. And option B, with the fluorine atoms forming stable CF covalent bonds, it is true, but sorry, but we're really looking into the intermolecular forces are what matter in this question. So when we talk about atoms themselves forming their stable covalent bonds, we're talking about the intramolecular forces, okay, within a single molecule, right? But when we're talking about melting point, that concerns the intermolecular forces, which is essentially two of these, but saying how they bond to each other. Okay, and this bond is telling us about the intermolecular forces. So the way to remember that is think of inter as between molecules, but intra is within molecules. Okay, so we have one molecule, and within that molecule, we have this intramolecular force. Okay, but within this intermolecular force, we have these two molecules interacting and having a force between each other. That is the main thing that impacts on melting point. Okay, especially because we have this tetrafluoroethene structure, poly referring to many. Okay, so if we want to figure out why a poly versus another poly, which is also many, has a higher melting point, well, we can sort of see that, well, which is this one right here. So this is polytetrafluoroethene, where we have CF and then that's polymerized. Okay, so we have many of them. Then what essentially talking about the intermolecular forces, we have this another one of these tetrafluoroethene to make poly of them. Okay, and we're really just talking about the intermolecular forces, as I circled in green here, between them. Okay, so yeah, so basically what I'm trying to say is that um, we look more into the intermolecular forces because we're talking about big compounds, and differences in intramolecular forces aren't really going to change much or have an effect on melting point. The point of temperature at which um, the compound or substance will fully melt, right? So yeah, again, as I'm stressing, melting point, boiling point, those sort of things are impacted by intermolecular forces, okay? So it's either going to be C or D because dispersion forces in dipole-dipole interactions are intermolecular forces, okay? Now let's see here. Um, Dispersion forces between closely packed fluorocarbon chains. Yes, that is true because we know that um, the packing, so I'll circle that because that is the answer, but we know that the packing of large fluorine atoms leads to stronger dispersion forces, which leads to a higher melting point. Okay? And we can notice that because in terms of whether how we know it's a nonpolar or sort of um, compound is because we have C. Well, it doesn't actually need the ionization or energy, sorry. We just sort of have to know about the structure of these polyesters and things like that, or like polymers, sorry, not polyesters, 'cause that just involves an ester. So the polymer, which is a basically, I think fluoroethene will require a double bond here. So I think that's what it is. Yeah, sorry about that. I think that's the proper way because we have an ethane, which means we should have these, I believe. Yeah, but either way, it's still the same sort of meaning, about the intermolecular forces, which is why we can cross out A and B. Um, yeah. So, yeah, as I was saying, the packing of those large fluorine atoms leads to a stronger dispersion forces and increase the melting point. And we know that polytetrafluoroethane polar because of a symmetrical structure. Okay. So even though we know from the formula sheet that the electronegativity of carbon and fluorine is significantly different, the fact that we have this sort of symmetrical line makes it actually non-polar. There's no polarity between the C's and F's because we have them sort of equalizing to each other on both sides, from left to right and also top to bottom. Okay, we can see that we have, you know, two F's on either side, um, and sort of the carbons are split, like how you want it to. So if we were to, I guess, say, create polytetrafluoroethane in like one of those 3D models that I'm sure that you've used in class, if we were to try and, I guess, twist and turn it around, it's pretty rigid because of the um, non-polarness, or like it's more compact with that due to the dispersion forces, and that's what it represents really in the 3D model, is we have really strong um, intermolecular dispersion forces between non-polar molecules um, and stuff. So That's my method of knowing it. It is a pretty difficult question. Um, I did get it wrong on the um, on my actual paper, but it was a difficult question. And it's quite difficult to understand. But I'm trying my best here, and I hope that it can help in some way. I can also try and help by canceling out why it can't be D. So I'll explain that a little bit. So we know that PTFE is nonpolar overall, right? We've talked about that. And so the dipole-dipole interaction will actually not um, dominate here, right? It the thing that is dominating, or the forces, is the dispersion forces, okay? So that's why C is the better answer. But I know for a fact that I chose D in this and got it wrong. So I also make sure that I'm looking at the marking guide and everything for the QCAA, because I need to make sure that I'm giving out the correct answers and I'm just not just justifying something that I believed was right. But I hope this can give a better explanation on why I I think that it's C, and how I can better um explain why. And what I'm really trying to do is just create a working out sheet for the multiple choice answers, because QCAA doesn't provide them. So I'm trying to, support those students who wish to learn something out of these past papers in the multiple choice. First off, question 10. The acid dissociation constant Ka represents the pH of an acid solution, not necessarily. Okay. The strength of an acid solution, yes. Okay. So immediately when you think of Ka, think of strength of acid solution. Okay. Um, you know, in terms of the pH of an acidic solution, it's related, but not the definition. Okay, because we know Ka is just the negative log base 10 of um, sorry, Ka is 10 to the negative pKa. Yeah, that's on the formula sheet, I think, as well, or maybe a derived version of it. Uh, yeah, so we can see here that we have well, we'll just try and derive it. So we know that something with a pH or P something is equal to the negative log 10 of that concentration. Okay, so it's the same thing here in terms of this equation. We have a pKa equals negative log base 10 over Ka, sort of concentration or constant. And so if we just divide by -1 both sides to get rid of this negative here, and from the log we have negative pKa equals log base 10 to Ka. And then we know that by Matt's log laws, that, or the sorry, changing this to an index form, we just take the base, raise that to the power, which is equal to, and then negative pKa, and that's equal to what's in the brackets for what we're logging, Ka. Okay, that relates to, equals back what I said originally. Okay, so yeah, it is related, but it's not the definition. Okay, we have to use it in a formula to get to it, but it's not saying that um, Ka is not equal to pH, right? So that's why it's not A. C, concentration, Ka is independent of initial concentration. So it is not C, because Ka is talking about concentration of an acid solution. No, Ka is independent, as I said, of initial concentration. D, conjugate pairs. No. The Ka is actually just a value. It's a number, really. So if I were to, and the number is usually like a 10 to negative something, like a decimal. So, I mean, to say that we have 10 to the negative something conjugate acid-base pairs is a pretty weird number to say. Pairs, we're literally talking about like whole numbers, but Ka is very rarely a whole number. So, I mean, that's another way you can um, cancel that out. But it's really about the strength of the acid solution. Um, it's yeah, like Ka would be um, less for weaker acid, weaker acids, and Ka would be higher for stronger acids that dissociate more. And by dissociate, I mean like, separating their H pluses and their um, other parts of like breaking apart their acids, H plus ions, cations. A Bronsted-Lowry acid. This is a typical question here, so just note that acid donates. So acid donates and bases accept. Okay. So I don't know, ADBA, whatever you want to remember it. Acids donate a proton to form its conjugate base. Okay. That is there. Right? It is not B because we're not donating a proton to form its base. Bronsted-Lowry acid will always turn into a conjugate base because it wasn't the original base that was combined together. Question 12. The following equilibrium law expression is given for a specific reaction. So we have the Kc equation here, and we know that the formula for Kc, as is in our formula sheet for chemistry, under chemical equilibrium systems, is first one here, Kc equals the concentration of C to the power of C, and then concentration of D to the power of D over concentration of A to the power of A and concentration of B to the power of B for this reaction here. So we can see that we're just taking the concentrations of these capital letters and raising them to the power of what is on the number of moles in the front. Okay, so essentially what happened here is that we have a 1 in front of here. So if we have the products, concentration of products to their number of moles, so we have concentration of products to the power of moles for each of those products, the multiplication of them, and then the reactants, same thing, number of moles. Then we can see that we have the top part of the fraction as our products, all right? And so we can easily say that it's either H2O or CO2. But remember that when we're talking about Kc values for equilibrium law, then we have to only consider gaseous states, which is lowercase g, and aqueous states, which is AQ. And the reason for that is because these types of matter can change in concentration, okay? Because we know Kc values can change given the different concentrations of the states, all right? So pure water, which is a liquid, and other, pure solids as well, they cannot change in concentration. And so they're technically not included as part of a significant part of the Kc value, okay? So if we were to choose between A and C, we would choose A because it's a gas, all right? And so you usually just go for the gas or the aqueous part of the law expression when it asks you which of the following is a product of the reaction, okay? So yeah, it really just depends on you knowing that Kc is only affected by the gaseous and aqueous types of matter, right? Because they can change in concentration, essentially.
So question 13 to 14 is talking about two reactions as shown, and question 13 is asking to determine the type of reaction that produced compound X. Now we know from the GAA syllabus we have these pathways which we have to memorize off by heart. We know that if we have an alcohol, such as recognizing this group here of the OH, so we know it is an alcohol, and we significantly add heat and reflux with this H plus and dichromate ions, then we get straight from a primary alcohol, which is what CH3 CH2OH is, all the way to a carboxylic acid. All right, and we know that that follows the oxidation reaction pathway type. Okay, another way to know that is, since we know that there's an exchange of H plus and O and oxygen, so that's going to change the oxidation number, so therefore it is oxidation. So question 13 is B. And question 14 is asking us to identify the compound Y. All right, and we can have a look that if we just substitute compound X as, so we know that in reaction 1 the alcohol here is ethanol because there's 2 carbons, so therefore we're going to have ethanoic acid as a compound X, so we can copy that on here. And then if we're adding this right here, which is an amine, specifically methyl amine, because we have a methyl group here, then we can see that once we put lots of heat greater than 100 degrees Celsius and we put this like sort of catalyst here, then we will get compound Y, which will be an amide, because again we have a carboxylic acid with an amine. Those combine to create a condensation reaction to form an amide. Okay, and we remember amides are just basically with the NH, but they have an O, an oxygen group. So we can tell that that's going to be B, because we have that amide sort of group there, which determines that this is an amide. All right, this one would be a nitrile, okay, because it only has one N at the end of the carbon. This one will also be an amine, so those cancel out. And this one, this is like a carboxylic acid with an amine. It's not really a well-defined thing we learn in year 12 chemistry. So the best answer is B here. Okay. Question 15, identify the single displacement reaction. All right, so we know that single displacement reactions are really just about, we have compound A, and then that's attached to like BC. So two compounds together, that forms AC plus B. Okay, so we're essentially in single displacement, we have a single compound, and then these basically swap in which one is our combined. So this is left over here, all right? So with option A, we know that it's just a sort of addition or like combination reaction. It doesn't really give us two parts, so there's only one part copper and oxygen here, which makes a two-part substance, so that's not it. B, we have a two-part substance, but then it sort of breaks apart, decomposition reaction into these different parts, so it's not going to be that. We have an A part here, so just one element, and then we have two sort of different parts here, and then they actually swap here to make that, and then we're left with just our single AG. And so that is our single displacement reaction. Okay, this right here would be a double displacement reaction, because we can see clearly from our formula of the single displacement that we are having like two compounds here and then two compounds here, right? And then they basically swap places from here to here. They literally, just alternate, swap places, right? So we know that that's not going to be a single displacement reaction. This is a double displacement. Okay, so it's not D, right? So that leaves us the only option as C. Question 16. So this was actually a difficult one. I think I got this question wrong. So I got two questions wrong in the multiple choice for chemistry, but I'll do my best to try and explain why I think the option, the answer that KCAA gave was the answer that they gave. Okay, so we can immediately look and see, do all of these, we can quickly see or calculate what the value for X will be in terms of the number of hydrogens, because we know that 86 right here is a key number. It's actually the molecular ion peak, which we refer to as M/C, M/C, and that tells us the overall mass of the compound. So if we have in our formula sheet, we can see on page 4 the mass of carbon is 12. Okay, so we don't need to use these decimals because we're using mass spectrometry, which uses whole numbers. Oxygen is 16 and H is just 1. Okay, so if we keep that in mind or just memorize that, then we can calculate 5 carbons are going to have 12 times 5, and 1 oxygen is going to have 1 times 16. Okay, so we have 60 and 16, just doing some quick maths there. Adding that, we'll get to 76. So what's left over for the 86 total mass? It's going to be plus 10 hydrogens, because we know that the mass of one hydrogen is 1, so simply just adding the rest, getting the I guess the difference between the total we want and how many carbons and oxygens we have. We know that there'll be 10 of the mass left over, so that will be the 10 hydrogens left over as well. Okay, so we can immediately cancel pentane 1-ol, and I can show you how we can do that fast as well. So what I would like to do is I like to make the main structure of my pentane chain. So imagine I have an alkane, right? And I just like to do that first and then manipulate it a bit. afterwards. So I would suggest having a pencil. Obviously, you know, for multiple choice you use a pencil, but for working out also use pencil, and just basically erase one and like erase what you need to in order to change it into one of the options that you have. So we know pentan 1 all is not going to work because we're simply just adding an O here, right, in this end. So it doesn't actually change the number of hydrogens that we had initially in the pentane, which was actually 12. So if we count up the number of hydrogens, there's definitely not 10 hydrogens, okay? So that's definitely a no-no. So we can cancel out C. All right, so back to our normal alkane, pentane chain. We can look at option A now, okay? So option A says we have a pentan 2-on, okay? So pentan 2-on means that we're gonna have a carbonyl, in other words, C double bond to O on the second carbon. So say this was the first carbon, so this is the second carbon. And then we need to make sure that carbons only has 4 bonds, okay? Because due to the octet rule, because carbon on the periodic table comes on the 4th group or the 4th column. So if 1, 2, 3, 4th column, then that means that we can't have there's basically like 4 outermost electrons, which I think they're called valence electrons. And because we need a pair for our valence electrons, that means that carbon has 4 bonds it can make, okay? Or in other words, 4 empty pairs that it needs to pair up with, right? So that's why carbon needs 4 bonds, okay? And making sure again that every carbon has 4 lines. So we've changed the second carbon to have 1, 2, 3, and 4 lines, okay? So remember, double bonds make up 2 bonds essentially, hence the double bond, right? So now that we have this, we can check how many hydrogens we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And that matches our C5H10O, which is what we have up here, right? So this X, we found X is equal to 10, okay? Cool. And that would be the same for a pentan 3-on as well, for the because they're both ketones, they're just different areas within the middle of the chain, so it's not going to affect the number of hydrogens. You can check that yourself if you want to. And we can try pentan al, so the aldehyde on the end. We can check that. So that would give us this here. So I'm just rewriting it and putting, just instead of drawing the alkane again, I'm just gonna go straight to the aldehyde. So we have a carbonyl on the end of the chain, okay, as opposed to a ketone where it's in the middle of the chain, okay, which is why we need to write a number there for the pentanal. Sorry, we need to put a number for the ketone, but not for the pentanal, because it's always going to be pentan 1-al. But we don't really write that because an aldehyde already indicates that it's at the end of the chain, so it will always be the first carbon. All right. So we also know that the number of hydrogens that are there are 10 as well, so it also fits our formula. So that's doesn't really helpful. It's not really that helpful there. We have 3 options still. So how can we, I guess, eliminate one of the options? So we know both of these are ketones, okay, and one of these are aldehydes. So what if there was a way to cancel out that it was an aldehyde or a ketone? Okay, if we can cancel out it's a ketone, then we know it's definitely an aldehyde. If we cancel out it's an aldehyde, then we know that's going to be A or B, right? So the way to figure that out, I guess, is to not only look at the 86, but look at this big peak, right? That's called the base peak. It's the largest fragment. Okay, and note the number they also give is 71. Okay, so whenever you're given a mass spectrum question, always use the numbers that they provided for you, okay? Because they mean something. They're meant to distinguish, essentially, between option A and B or whatever, and making sure that you get the most accurate answer as possible, okay? So essentially, the reason we get the 43 is because we are trying to analyze fragmentation patterns, okay? So fragmentation patterns, if I draw this in green, is basically where I'm cutting certain areas, such as here, between the second carbon and the third carbon. I'm cutting that area to just measure the mass of this part and the mass of this blue part, okay? And then whatever is most common, that will end up as my mass, okay? So when we notice a mass of 43, that should ring alarm bells, basically, in saying that this is a classic acyl fragment. Okay, what do I mean by acyl? It's basically a CH3CO+. Okay, so I know it's a bit difficult to understand, but sometimes we just have to accept these things and I guess sort of memorize them by heart. But if you understand that 43 is like a, I guess key number that really strongly suggests the presence of this acyl fragment, okay? And the reason for that is if we just calculate the mass quickly for CH3CO+, we have 2 times 12 because 2 carbons, 3 hydrogens, so 3 times 1 and 1 oxygen. Then we make 24, 3, 16, and then if you want to plug in your calculator or do it in your head, that's 43, okay? The sum of all of that is 43, okay? So that's why it's important to know these classic fragments that you'll get and the, I guess, type of mass spectrum graphs you'll get, because it will help you to recognize whether it's a ketone and an aldehyde and stuff like that, okay? So what really is CH3CO+? Well, if we draw it out, we have a carbon and 3 hydrogens, and we have another carbon, and then we have an oxygen, okay? Oxygen plus. And what does that mean? Well, it's essentially just referring to this part here, okay? This part that I'm going to highlight both of them in purple just so you can see that part. So you can see that this fragment right here, which I've also made a division in green here at the bottom, that is what where the 43 is coming from. All right, it's the classic acyl fragment. All right, so that tells us that it has to be a ketone, okay? And I believe the reason why it can't be an aldehyde, which is this part right here, is because if we make a cut here, right, which I believe is more common, aldehydes, we just have to know, unfortunately, we just have to memorize this stuff, but it often gives a CHO plus at M/C equals 29, okay? If we want to calculate that mass, then we have a MZ of 29. And you can see that, 29 would be around here, but there's not really anything for 29. So, and this right here would be around 27. So that's definitely something we can't really get in an aldehyde, if that makes sense. If it was an aldehyde, we would have this thing to separate the carbonyl groups and the alkane group, but the mass of 29, which would be this circle in green, isn't really defined on this mass spectrum, so we can safely assume that it's going to be one of the ketones, right? And then from that we have to choose, is it pentane 2-one, which is what I've drawn here, or is it pentane 3-one? Okay, so basically I'm not going to draw it out, but we can sort of just say that pentane 3-one is less likely to produce that stable, again, classic acyl fragment because of the symmetry, right? So basically a pentane 3-one is just the third carbon in the middle here having that double bond O, but you can sort of tell just by looking at it that we can't cut off any section and simply have that classic acyl fragment of the CH3CO, because wherever we cut it, we are always going to have the side with the oxygen is always going to have 3 carbons. Okay, actually you know what, I'm just going to write it so it becomes clear in your head. Just checking I'm right there. So 3, 5, 8, 10. Yep, so still fits the formula, okay, for the pentane 3-one, but no matter where I cut it, if I cut it here, right, then there's no really possible combination. And remember, it's only one cut. I can't just make a cut here and say that, oh, I have an acyl group. No, okay, it's only one cut that you can make at a time. There's really no way I can just get the CH3CO because the O is in the middle. All right, so it'll end up us needing to use 3 carbons in that case. All right, so I hope that makes sense. But if you have any questions, again, just let me know, and I'm happy to further explain. But that's my reasonings for why question 16 is A, and that's also what UCAA has given out as the answer. So I'll see if I can quickly check. I'll just search up because they also show the percentage in the subject report of what people chose as the answer options. So I'm sure that in question 16 last year in their subject report, then they've definitely had something there. So just give me a second. Yes, so question 16, only half of people got pentane 2-one. Okay, so if you imagine in a class of 30 people, only 15 people would have got that mark, so it was a pretty difficult question there. All right, so question 17, identify the product produced at the cathode when a concentrated aqueous solution of NaCl undergoes electrolysis. Okay, so what really does the electrolysis of NaCl involve? Right, so what we have is we have an aqueous solution, so we just put the element, state of matter there, and it's basically a source of Na plus and chlorine ions, right? Now water in this electrolysis, which is present in electrolysis, at the cathode as well, it can also be oxidized and reduced. Okay, and I'll give you a tip for these sort of questions because it also tricked me, but I'm pretty sure I got this question right as well, and all the electrolysis questions, is that at the beginning of your paper one, like writing time into your formula book, because you can't write during perusal time, but at the start of your paper one writing time and paper two writing time, because your formula sheets actually get replaced, because obviously you can write stuff there. It just draw this arrow basically, which says that at the top, these are the things that get more oxidized. Okay, if they're at the top, they are the stronger reducing agent as well. Okay, and at the bottom, as you go down, they're more reduced. Okay, and the oxidizing agent. So a way to remember that is that at the bottom we get reduced, bottom reduce sort of thing, and then also, the more positive your E naught value, which is this one here, the more positive it is, the more you're gonna have a reduction in that element. So that's also the way to remember it. We have anions, like electrons. If we reduce a negative, then that becomes a positive value. So that's, I guess, what, in a way, sort of how you can memorize that there, in case you forget. And also write down the mnemonics. Okay, so I know about red cat, which means there's a reduction at the cathode, and NOx, which means the anode has oxidation. Okay, that always stands true no matter what. All right, whether it's electrolysis or electrochemical cell, anything, it's always red cat. And then same that always applies is oil rig. So oxidation is loss of electrons and reduction is gain of electrons. But for this question, it's not really that necessary, but it will help you with recognizing the relationship between electrons and oxidation reduction. But for this question, I'm really concerned about Na. So sodium. So I know this part is sodium. Okay, so what I'm going to do is, with a pencil, so I can erase stuff for other questions, is I'm going to circle this E naught value in volts. Okay, negative 2.71. All right, and I'm going to get chlorine. All right, so I know it's at the bottom here because that gets reduced. Okay, because if you think about NaCl, all right, we have a Na plus and a Cl minus. Okay, so that's why Na is getting oxidized, which was it's more up at the top, whereas Cl is at the bottom. Okay, and it's a negative there. So that's another way to remember it as well. Okay, so I'm gonna put a star on that and circle that value. Okay, and then I'm going to circle this part right here. So I put another star. I'm just going to circle this value, negative 0.83. Okay, you just have to be familiar and recognize with these sort of questions, so you can immediately know, I have to make sure I take note of this value. Okay, it's very important, and it will come up many times in many questions, especially in electrolysis where there is water in the cathode. Okay, it's just assumed that there's water in electrolysis there. So because especially in an aqueous solution, then there's usually water too. So that's another way to know. And so once we've circled those values, then we can sort of see, all right, well, we can have reduction in either this equation here that I've starred, the Na plus electron to the solid sodium, or we can have a reduction here as well, where we're basically reducing that this sort of, if this oxygen is -2, then this H2 is +1 each, so +1 times 2 is 2, and those cancel out neatly. But then here the hydrogen will have a 0 oxidation number, and so that's also a way we can reduce at the cathode. Okay, so just essentially know that reduction always happens at the cathode. So if we know red cat, okay, cathode, reduction, and so we need to think about which one is going to be more reduced between the Na plus and the H2. Okay, now we can see here that as we go more, so on our line that we made at the start of the exam, we know that the more we go to the bottom of the table, that's what gets reduced. Okay, so between Na plus and H2, or sorry, Na, just Na and H2, we know that H2 is lower on the table than Na, and therefore that is what gets reduced. Okay, so our answer is D. Okay, now it is a tricky question to wrap your head around, but the more practice you do and the more you do these past papers, you'll understand sort of the pattern here is that there's always a H2O, water in these sort of questions, and then you have to compare if one's going to be reduced more or oxidized based on where they sit on the table. Okay, because we know the E naught values are in order. Okay, they're not just random, but they're there so you can easily identify which one will be reduced. Okay, so the ones with a higher E naught value gets reduced, if you want to think of it that way, in terms of the E naught value, which is this value right here. Okay, that I've circled. Now if you want to talk through the other options, why they're wrong, well, we know that chlorine chlorine can be chlorine is actually oxidized. Okay, because again we had chlorine as a negative in the Na plus Cl, but this chlorine gas has been oxidized to a oxidation number of 0, right? So that's an increase in the oxidation number, so that's called oxidation, right? So sorry, I didn't mean to circle that, but we don't have chlorine gas. That's definitely not going to be the product produced. Okay, because in order to have something produced at the cathode, something has to be reduced first, right? So, and then another one is that sodium, the liquid, not really, especially given that there's a liquid here, it's a bit suspicious. But yeah, it won't really be produced in aqueous electrolysis because, as we said, it's too reactive, and water gets reduced instead. So another way I guess you can have a look at is the given that Na is really reactive compared to H2 is also a indicator there. It also proves that theory. And Option C, oxygen is actually formed at the anode, okay? From oxidation, of course, because, if we have H2O, then what's the oxidation number for oxygen? It's -2, okay? And then each H or hydrogen will have a +1 oxidation number, to times that by 2 and cancel out to 0 for the overall. But an O2 gas has an oxidation number of 0, so that gets oxidized, okay? And oxidation, we know from the mnemonic red cat and anox, oxidation occurs in the anode. Alright, so it can't be O. So therefore the answer there is D.
Okay, so question 18. We have 4 half cells, 1, 2, 3, and 4, with the electrode and the electrolyte solution, and we're basically trying to find which pair of these would produce the largest potential difference in volts under the standard conditions when combined to construct a voltaic cell. Okay, and so this would require the use of our formula sheet on page 10, where we have the standard electrode potentials at 298K, which would we assume as the standard conditions. Okay, so the first step is to figure out what the half reactions are involved, and therefore the E naught value for each of the half cells. So we know that for cell 1 we have copper, right? And the NO3 here, if we look at page 15 of the formulas and charges for common polyatomic ions, we know that NO3 is a minus here. And so you can sort of safely assume that this copper would be a copper plus to cancel that out. And so if you look at page 10 with the scanning electrode potentials in the equations here and try and find a copper plus, where could that be relevant? Um, it would be this one, so 0.52, right? So we have the copper plus an electron to the copper solid, okay? And so that's where our copper plus is with the charge of +1, okay? So we'll label that as the cell 1, and then we'll do the same for the second one, second half cell with Fe. Now, if we know that 1 NO3 is a minus charge, and we have two versions of that, we essentially get an overall charge of -2. So that means to cancel that out and have an overall charge of 0, because we're assuming that the overall charge is 0 for all of these electrolyte solutions because we don't have any oxidation number on the top right-hand corner. We know that this Fe is going to be 2 plus, and so we are trying to find that Fe2 plus, and we know that it's at this one right here with the Fe2 plus, and we have the value for that as -0.44. Okay. All right, next we have aluminium. Okay, so again, if NO3 is a minus charge, then three lots of those will give a -3. Okay, and then therefore this needs to be +3 for aluminium. Okay, so if we're trying to find the +3 aluminium, we look and find it up here. So this is the third half cell with aluminum 3 plus, and that's our E naught value for that. And the lucky last, the final half cell, okay, we can see that the electrolyte solution here has also a negative NO3, but then there's 3 lots of that, so -3 again, and then Fe, the charge for that will actually be +3 this time rather than 2 plus in half cell 2. So that means we have to be using a different standard electric potential formula and E naught value, which will be this one right here with the Fe3 plus. Okay, so that's number 4. Right. So essentially what we're doing now is we're trying to find which pair of these gives the greatest distance between um, them on the table. And the reason we're trying to find the greatest difference is because we need to recognize a formula. I don't think it's on the formula sheet, but I'll double check. No, it's not on the formula sheet. We just have to memorize this formula. But this is also something you can write down in, as I said on the formula sheet during the start of your writing time, is that the E naught of the cell, sorry, E naught of cell is equal to E naught of the reduction minus the E naught of the oxidation. Okay? In other words, we're trying to find the E naught of the cathode because red cat minus the E naught of the anode because anox in our mnemonic that we've have up here. Okay? And so basically what that means is if we have what is reduced, which would be um, the more of the bottom values, and we minus that with a negative E naught that's more at the top. So pretend we recognize that the largest distance is 3 and 4, right? And so if we did put 3 and 4 in the pair for the voltaic cell, each of them being a half cell, we know that the reduction will be the equation at the bottom of the table, which will be the Fe3 plus to the Fe2 plus, okay, which we know will be 0.77, all right? And then it'll be minus this negative value here, negative 1.68, okay? And so if you put that into your calculator, you'll get a value of, I'll just do this in my head real quick. It'll be around 2.45, okay? So that, if you want to check yourself, but I guess the easiest way to go about this is looking at the table visually and seeing what's the greater distance because the E naught values anyway go up from the smallest, negative value to the largest positive value from top to bottom. So, the greater distance they are on the table, the half cells, then we know that their difference is going to be the greatest, okay, which is what our formula is saying for the E naught cell, okay? So our answer there would be D. Okay, so that's a faster way of going about it rather than doing each and every one of those combinations from A to D, but you can definitely do that and it will still point out there. Cool. Right. Question 19. Esters undergo hydrolysis to form a carboxylic acid and, okay, this is a nice easy one. You just have to memorize your pathways for this. So if you know this green type of reaction pathway type is a condensation. There's really only two types, okay, which involve a carboxylic acid as and the combination of one of these alcohol or an amine, okay, to either an ester or amide respectively, okay? So it's not that difficult to memorize, you know? So condensations we know, um, because well, it's assumed that we know that a condensation is the opposite of a hydrolysis, okay? So basically what a hydrolysis is doing, if I draw this in blue, um, a hydrolysis is basically saying that I have the condensate product of the condensation reaction, but I'm just doing it reversed, okay? So I'm just doing the reverse of a condensation reaction. That's what hydrolysis is referring to. Okay, so esters undergo hydrolysis to form what? Carboxylic acid and alcohol. So our option there is C. Okay, and then last question, identify the polyprotic acid. Okay, so polyprotic acid means basically an acid that can donate 3 hydrogens. Um, you know, um, but they need to be attached to obviously like a proper end of the hydrogen. So you know with acids they need to like have their hydrogens hanging off in the end, sort of, if you like to think of that, if it that of that think of it that way. So it can be easily able to be donated. Okay. So what I mean by that is um really like if we think about drawing out these structures, so H3PO4, for example, um, we have P double bond to O, and then we have the 3 other O's have a H attached to them, okay? And these individual H's, because they're single bonded to the O's, they can easily be donated, okay, to other substances or dissociate, okay? Um, just a key thing that was in your syllabus, like from the 2019 cohort up until the 2025, um, sort of like the 20. So that what happens in KCAA at the moment is that the 2025 year 11s have a new syllabus, but it's usually about the same, but it's not exact, and this may change, but essentially, in your syllabus for the 2019 version, we have to, one of our dot points is to understand that acids are substances that can act as proton or hydrogen ion donors and can be classified as monoprotic or polyprotic. Okay, so if we just remember these key prefixes, mono meaning one, protic as in like the, protons or like hydrogens, H pluses, if you like to think of them, and poly meaning many, and again, protic is just the same, depending on the number of protons donated by each molecule of the acid, okay? So as I gave the example of H3PO4, we have 3 hydrogens to, donate. And so that's why the answer here is B, indeed. Um, and, we can cancel out the other options as well. NH3, that's a common base. It's actually a weak base, okay? Because yeah, sure. There's 3 hydrogens, which makes poly, because poly we usually talk about at least than or greater than 3 hydrogens, because we know that if there's 2 hydrogens that can be donated, that's a diprotic, di meaning 2, and then if there's only one that can be donated, that's a monoprotic. Okay, but um, I guess it's just common knowledge that NH3 is not really an acid. It can't really dissociate into um, like as well as H3PO4 can into like H2PO4 plus H plus. Um, and another thing is that in chemistry, when you write out the compounds, what usually happens is that the acid is usually coming first. So H3 is the part that's the donating part that comes first in our nomenclature or how we write it out basically. So um, that's really something to keep in mind there as well. So if we have immediately just a H3, then we know that's it. It's at the end and it can easily be donated and that sort of stuff. So we have three hydrogens, and so we just can tell that B is the polyprotic acid. But I guess another way to go about this is being very familiar with the different types of um, classifications of acids. So we know a monoprotic would be like hydrochloric acid, because it has a H plus and a Cl minus hidden in there, which we have, we can just like take out the H. We have H2SO4, which is a diprotic because we have a H2, each H is a plus, but given there's two, we have a 2 plus charge and SO4 is a 2 minus charge. And then H3PO4 is obviously, as we said, is polyprotic. Okay, if you're wondering the names of these, we have hydrochloric acid, right? And then H2SO4 is sulfuric acid, and H3PO4 is phosphoric acid. Okay, so those are really the typical um, examples of each classification of the acids in terms of how many protons it can donate. So just keep those in mind, I reckon, and maybe some others that you find online. Maybe um, memorize two more examples in each type, just so you're really familiar with the um, I guess, pattern of knowing which ones are which and how to distinguish between them. Obviously, C, we have NH4, which is more like a base sort of thing. Ammonia is really a base. You just have to know that ammonium, ammonia, and then three versions of that will have, well, 12 hydrogens in its overall chemical structure, and that's like way too many. Um, Realistically, it's not going to donate 12 hydrogens that it can its maximum. Same with this. This is really like what is that, ethanoic acid, but I think that's a pretty weak acid as well. It's not a really strong acid, and you can't really say that you're going to donate these three hydrogens because those are at the end of the structure. They're within the middle between those two carbons, so it'll be a bit awkward there. But yeah, the clear defining feature of a polyprotic acid is just this H3 at the front there. But yeah, that's really it. So that is the paper, and I hope you got something out of this, and best of luck. Thanks for watching.